Okay guys, tonight we're going to talk about Earth's structure and as well as the theory of plate tectonics. This first slide is a review. So these are the three main layers of Earth: the crust, the mantle, and the core. So that's not new information for you. You have information on all of these layers in your foldable that we created last week. So we can divide the three main layers of the Earth down into physical structure layers, and there are 5 of them. You'll notice we have the lithosphere, we have the asthenosphere, the mesosphere, the outer core, and the inner core. Now if you look at the diagram, the line that you see, the pink, blue, green, brown, and white, the pink line is showing you how deep the lithosphere goes, and if you'll just kind of make a mental note that that pink layer should go into the upper mantle. It should not just stop at the crust. So that's a mistake on the diagram's part. It needs to go a little farther into that blue line. But that shows you relatively how deep those 5 physical structure layers go. Okay, so the theory of plate tectonics is that the Earth's lithosphere is divided into sections called tectonic plates, and those plates are sort of floating on the mantle, which is specifically the asthenosphere. So if you look at the picture on the left side, the lithosphere is the raft with the person sitting on it, and then the asthenosphere is the water underneath it. So if the water moves, then the raft is going to move on top of it. So think about currents in the ocean. If you don't have a motor or a sail on a boat and you're just sitting in that ocean in some kind of a raft, then you're at the mercy of the ocean current. Wherever it goes, it's going to carry you with it. So that's what happens. The continents are the lithosphere that's sitting on the asthenosphere, and when the asthenosphere moves, it carries the continents with it. Now if you see the major plates that are on the right side there on the map, those red lines are the plate boundaries. So those are the edges of the plates that exist. Now they're sitting right next to each other, and as the asthenosphere moves and the plates try to move with the asthenosphere, then they're going to bump into each other, they're going to pull apart, or they're going to slide past each other. When they do that, rocks tend to break and we're going to get earthquakes, and if anything starts sinking and going back to the mantle, then we're going to get some volcanoes that form. So we have 3 different types of plate boundaries. So there's 3 different options that 2 plates can do when they're next to each other. So as the asthenosphere moves, those 2 plates can either slide past each other as in a transform boundary, or they can pull apart at a divergent boundary, or they can push together at a convergent boundary. So we're going to look at each one of those types of boundaries specifically, starting with the transform boundary. Okay, so transform boundaries is when you just have 2 tectonic plates that slide past each other. Notice the crack between them is the actual boundary between the 2 plates. Now in this case, crust is not created and it's not destroyed. In order to create crust, magma's got to be coming up somewhere and cooling into igneous rock, and that's not happening here. It's not being destroyed because in order for that to happen, something has to be sinking back to the mantle and melting into magma. So we have no sinking here either. They're just sliding past each other. So when they're sliding past each other, the edges are not smooth, and you can look at the San Andreas Fault picture there in the left-hand corner, and you can see that the edges are jagged, and so they're going to catch on each other as the plates are trying to slide past. When they catch, when stress builds up, eventually they snap, and you have shock waves that are released in forms of earthquakes. So transform boundaries is where we tend to have most of our earthquakes. Specifically, we have one that goes right up through California. That's the San Andreas Fault. So that's why California has all of those different earthquakes daily, just about. Okay, divergent boundaries. This is where plates pull apart. This is happening at seafloor spreading. So we talked about divergent boundaries already without giving it the name divergent boundaries. So when 2 plates pull apart, it leaves a gap in the middle, and that gap allows magma to come up. So the gap has a name. It's called a rift valley, and the examples that you're seeing on the screen here are continental plates pulling apart. Okay, when we talked about seafloor spreading, it was oceanic plates pulling apart. Regardless, that crack widens in the middle and it allows magma to come up, and if magma is going to be able to come up, then you're going to get some volcanoes that form, and in the case of seafloor spreading, you're going to get brand new ocean floor. Okay, convergent boundaries. This is the trickiest one of the three. So this is when you have two plates that are pushing together. Now if you remember, we have two different types of crust. We have oceanic crust and we have continental crust. The oceanic crust is denser and heavier, so anytime it hits something, it's going to go down back to the mantle, which means there's sinking, which means it's going to melt, which means it's going to have magma that works its way back up to the surface, and you're going to get volcanoes. So anytime an ocean plate is involved and it hits something, you're always going to have volcanoes that form. Continents are light, they're less dense, so anytime they hit something, they always go up. So if they're going up, nothing is sinking, nothing's melting, no magma, so you're not going to get anything but really earthquakes when that's happening. So our three types of convergent boundaries that we can get are an ocean-ocean collision, that's two oceanic plates colliding. We have an ocean-continental collision, so oceanic plate is colliding with a continental plate. And then we have continental-continental collisions, which continental plates are colliding. So depending on which one is hitting which, we're going to get different landforms that occur. So the first thing I want you to pay attention to is the word subduction. It's in red on the screen. Subduction is a fancy scientific word for sinking. So anytime anything is sinking, specifically it's going to be an oceanic plate, and you're going to get magma that forms, and you're going to get volcanoes. Okay, so the valley for number one, for ocean-ocean collision, the valley between them where both plates are sinking is a trench. Okay, that's what it's called. It's an underwater valley where ocean floor is sinking back to the mantle, and it turns to magma, and then magma rises always. It's less dense than any other rock around it, so it works its way to the surface and you get volcanoes. Number two, you have an ocean-continental collision. So if you follow the arrows, the blue arrow is the ocean floor sinking underneath the green arrow, which is the continent. So the continent rises above, but again, you also get a trench there because ocean floor is sinking, so that's an underwater valley. And then you get magma that forms with a volcano that's on the continent. Continental-continental collision, you end up with plain old mountains. That's it, just plain old mountains. So the two continents hit, they're both light and less dense, so they go up. So what you're watching here is an animation of an ocean-ocean collision. Now, on the left side, you really should see that oceanic plate sinking as well, but just pay attention to the fact that as that one oceanic plate on the right is going under, the red dots mean it's heating up, it's melting that oceanic plate in the mantle, so it gets hot, magma rises up to the surface, and you're going to see a volcano form. Okay, so there it is. Here's ocean-continental collision. So the oceanic plate is sinking underneath the continent back to the mantle where melting is going to happen. So you're going to see the red dots as it starts to heat up. And then I want you to notice how thick the continental plate is compared to the oceanic plate. Still less dense though, it's light. It's going to go up and over the oceanic plate. So now we've got the melting going on. Now that magma is rising up through the continental plate, which means you're going to get another volcano. And there it is. Okay, the continental-continental collision, you can type in that website that you see there and see an animation for how it works. But the Himalaya mountains that you see the picture of right there are when two continental plates have been hitting each other. India is crashing into the Asian plate. So as they continue to crash together, those Himalaya mountains are growing by 1 to 2 inches taller every single year. So unless that plate reverses direction and they start pulling apart or moving some other direction, they're going to continue to grow taller and taller and taller as long as those plates keep coming together. Okay, so how do the plates move, or what is going on in the mantle to make them move? And the answer for that is convection currents. Now, we talked about the lava lamp in class. So hot wax at the bottom gets heated by the light, it rises to the top of the bottle, it cools, and then it comes back down to the bottom. So that's what's happening to the hot rock in the mantle. It's being heated by the core, it rises to the surface where it cools, and then it sinks back down into the mantle where it's reheated and where it rises up again. So it creates this circular motion underneath the lithosphere. So the plates are made of the lithosphere, so when the asthenosphere moves with these convection currents, then it carries the continents with it on the lithosphere. So this just shows you an animation of what it would be like. So here's Earth's core. That would be like the light in the lava lamp, and then it's heating up the rock. You see the red arrows rising up. As they get to the top, to the surface where plate 1 and plate 2 are, it cools and then it goes back down into the mantle. So if you follow the direction that the convection current circles are going, you can see that plate 1, if it was following the asthenosphere, is going to eventually move left with the arrows. Okay, that circle's going counterclockwise, so it's going to go take plate 1 to the left, and it's going to take plate 2, it's going to follow that circular motion on the right, so plate 2 is going to travel to the right. So if plate 1 is traveling left, plate 2 is traveling right, then you're going to get a divergent boundary there at that boundary line in the middle of plate 1 and plate 2. This picture is just showing you a diagram of what's happening with the convection currents and how it affects the ocean floor and the continental crust. So you can see kind of in the middle of the diagram where the arrows are going up to the surface, the oceanic surface. As it rises up, it spreads apart just like the simulation did in the last slide, and it pulls apart and you end up with a rift valley. That's the crack on the ocean floor called a mid-ocean ridge. That's where the magma comes up. Okay, it's cracks where the magma can come up because the two plates are pulling apart. Now, if you follow the oceanic crust to the right, then that ocean floor is eventually going to hit the continent. It's going to sink under the continent where that rock's going to heat up in the mantle and rise back up and give you your volcanoes. If you follow the rising rock in the mantle and then follow it to the left, you see that there's an ocean plate there that is going to hit another oceanic plate, and they both sink. So that gives you a trench, and then you can see the volcanoes on the left side of the picture that are formed because of that. Okay guys, so that's it. Make sure you bring your notes tomorrow so I can check you off for having your homework done. Have a good night.